Alright, continuing chapter 1 now, we are going to move on to measurements and units and talk about those. Alright, so measurements involve usually a number and some sort of unit. And the unit describes what kind of measurement it was, right? So if I go to the doctor and I step on the scale and it reads 245 pounds, it gives me two things, right? It gives me the value, 245, and pounds. It's telling me it's weighing, that number is my weight, right? Because it's pounds. And then I measure my height, 6 foot 3 inches. And the numbers again tell the value, and the feet and the inches tell you that they're measuring my height, a length, right? So, in measurements, it's going to be important that we have both a value and a unit, because the value tells you how much and the unit tells you what it's measuring. Height, weight, volume, whatever. Okay. So we're going to also be concerned about what system we're using for measurements. For science, we use the metric system because the rest of the world does that, and we want a common system so that when we report things, everybody can understand it, right? So we're going to look at two systems as we go through this, the metric system and the English system, and kind of see the benefits the metric system brings, especially when we're talking about science. Okay. On the little table here, or the little graph here, we can see a series of length measurements, or size measurements, that are distances, and they go from kind of a human size, a pretty, I don't want to say big, but big compared to, a blood cell, where the human units are meters. Meters are units of length, and a drop of blood is 1 millimeter in diameter. So we can see that meter is still there, but now we have a prefix, milli, which means millimeter is smaller than a meter. If we go down to the size of a blood cell, it's a micrometer. That little strange shaped U is micro in Greek. Again, we still have that meter base unit, but now we've got a different prefix, which makes it smaller yet. We go down to nanometer and picometer. So you can see the metric system uses that base unit, that length, meter, and then simply adjusts the size of it using the prefixes. Which is why we use the metric system. And those prefixes are based on base 10. So like a millimeter is 1/1000th of a meter. So if you take a meter and slice it up evenly into 1,000 pieces, that would be a millimeter. 1/1000th of a millimeter is a micrometer. 1/1000th of a micrometer is a nanometer. 1/1000th of a nanometer is a picometer. Right, so the metric system is kind of nice because instead of giving me a different unit for each length that we have, like we do in the English system where we have like inches and feet and yards and miles, they simply adjust the prefix to adjust what size the measurement is. All right. Like we said, we're going to look at units, and units we're going to look at both the metric and the English system. Where the metric system is going to use kind of these base units, grams for mass, liters for volume, meters for length, where the English system is going to use all these different units to describe different things, right? So ounces, pints, quarts, gallons, all those units are for volume. Inches, feet, yards, miles for length, and so on, where we have a different name for each different unit, or each different type of measurement. Okay, so we're going to be concerned about these things called SI units, and SI units are units that are assigned by this group called the International Bureau of Weights and Measurements, and they're the one that defines what units mean, how big they are, and they're internationally accepted, and they deal with all the metric units. So they define what a metric unit is, and then it's based on, if we have a different system like we do, we have an English system, it's based on the U.S. system of weights and measurements to define our units compared to the metric units. Okay, and there are there are 7 SI units that we can use to get all other units in the world, or all other units of anything. Okay, we're going to be concerned about 4 of them, well, 5 of them moving forward a little bit, but 4 of them for now. The metric unit of length is called a meter. Okay, so every unit of length in the metric system has meter in it. It may have a prefix on it, like kilometer, which is 1,000 times bigger than a meter, but it still has meter in it, which tells us it's a length. The metric unit of mass is a gram. Again, it can have prefixes on it, like a nanogram or a picogram or a kilogram, but it still has gram in it, which tells us it's a unit of mass. The unit of volume in the metric system is a liter, and the unit of time is the second. Okay, not minute or hour; those don't work in the metric system, but seconds do. Okay. The metric system, like we just said, got a little ahead of myself, uses prefixes to scale the units, and we'll talk about that here in a second. But every unit of length has meter in it. Okay, like centimeter, that's a unit of length. Millimeter, that's a unit of length. The volume always has liter in it. Milliliter, gigaliter, megaliter, microliter. All those are units of volume because they have liter in it. Okay. So this is the metric system. This is the prefixes. Some of the prefixes, basically the ones we'll see for during the semester, and this is the prefix defined as how that prefix is related to the base units. Okay, and we just said the base units are meter, gram, second, and liter. Okay, so these prefixes can be used for all those. So you can see in the middle here, right here, we've got prefixes for quantities smaller than the base unit are below this, and prefixes that for quantities larger than the base unit are there. Okay, and the prefix, the symbol for the prefix is shown right here. So for example, if we were doing units of length, we would have meters, and then anything below this line, for example, deci, a decimeter would be described as dm, prefix would be dm, and a decimeter is 0.1 meters. So basically that's saying if we take a meter and separate it 10 times equally, each one of those would be a decimeter. Okay. Centimeter is 1/100th of a meter. So if we took a meter and separated it 100 times equally, each one of those little pieces would be a centimeter. Okay. So this table gives us the prefix and what the prefix means. Okay. So like kilo, if we're doing meters, kilometer would equal 1,000 meters. Okay, that's what it's saying. And we can see that we're going to start to use these things where we have the 10 raised to a certain power. Okay, so let's talk about that for a second. It's called scientific notation. And we're going to use scientific notation in science when we have very large or very small numbers. And we do that so we don't have to write a bunch of zeros, because if we have a number with a whole bunch of zeros, it's really easy to add a zero or drop a zero accidentally when we're copying the number. So instead of doing that, we use this thing called scientific notation. And the fundamental, general way of writing scientific notation, a number in scientific notation, is in this form, where we have some decimal piece here times 10 raised to some power. Okay, go back a second. So scientific notation is in this form. Our normal form that we normally write numbers in is called decimal notation. Okay, so in a scientific notation number, that is going to be the format, always. Okay, and in this format, for correct scientific notation that we're going to use, the x has to be values from 1 to 9. That x can be 1, 2, 3, 4, 5, 6, 7, 8, or 9. Nothing else. It can't be a 0. It can't be a 12 or a 30. Okay, that number in front of the decimal has to be somewhere from 1 to 9. That one of those integers. That's it. Okay, there can be negative in front of it. That doesn't matter. But that x value, the number before the decimal, has to be one of those numbers. Okay. After that, if we need it, we'll put the decimal and then more values. Okay. That doesn't have to be there. We simply could write 5 times 10 to some power. Okay. We don't need the decimal piece to be in scientific notation. But if we do need it, then we can have the decimal, and y can be anything. Right? The last thing we need to talk about is n. N has to be an integer. It can be negative integer, so negative 1, negative 2, negative 3. It can be 0, or it can be a positive integer, 1, 2, 3, 4, 5, whatever. Okay? But n has to be an integer. And we'll talk about the positive, negative pieces here in a second. Okay? So that n means the number of, we're raising 10 to the nth power. Okay? So when we do that, it simply means when we raise something to a power, it simply means how many times we multiply 10 by itself. So if it's 10 to the first power, we write it as just simply 10. Multiply 10 by itself once. 10 to the second power, or 10 squared, is 10 times 10. Multiply 10 by itself twice, which is 100. 10 cubed, or 10 to the third, 10 to the power of 3, means 10 times 10 times 10, which is 1,000. 10 to the sixth is 10 times 10 times 10 times 10 times 10 times 10. I think that was 6. Which is going to be 1,000,000. Okay? The power tells us how many times to multiply 10 by itself. 10 to the 0 is defined as 1. Okay, so anytime you see 10 to the 0, that's just 1. Now, if we do negative numbers, if we remember, negative power simply means put that value in the opposite part of a fraction. So, for example, 10 to the negative 1 means put 10 to the 1 in the denominator. So it means 1 over 10 to the 1, which is 1/10. Remember, when we multiply by 1/10, so if we multiply by 1/10, that is simply dividing by 10. So if we multiply something by 1/10, or we divide it by 10, it's the same thing. All right? So 10 to the negative 2, that's 1 over 10 squared, right? Because that negative tells us put in the denominator. So 1 over 10 squared, so that's 1/10 times 1/10, which is equal to 1/100th. It's actually equal to 1 over 10 times 10, which is 1/10 times 1/10, which is 1 over 100, which simply means divide by 100. Okay? 10 to the negative 3, it's 1/10 times 1/10 times 1/10, which is 1/1000th, which means simply divide by 1000. Okay? So you can see when we have 10 to the positive power, we're multiplying by 10 that many times. And when we have 10 to a negative power, we're going to divide by 10 that many times. What we're simply doing is shifting the place where the decimal is. Okay? And like I said, multiplying by 1/10 is the same as dividing by 10. Multiplying by 1/1000th is the same as dividing by 1,000. Okay, so since our number system is based on tens, or base 10, the times 10 to the nth part simply shifts the decimal that many places. So if we have 10 to the third, it's shifting the decimal 3 places to the right. It's making the number bigger, larger, 1,000 times, by 1,000. Okay? And if it's negative, we're shifting to the right, or to the left. We're making the number smaller. So 2 times 10 to the third is, or 2.5 times 10 to the third is 2.5 times 10 times 10 times 10, because it was times 10 3 times, right? So basically we're moving the decimal 3 places to the right, which is, if we have 2.5, we move it 1, 2, 3, and we get 2,500. 2.5 times 10 to the negative 2 means we're dividing by 10 twice, so we're moving the decimal to the left twice. We're making the number smaller. That negative value means we're making 2.5 smaller by 100th. So 2.5 times 10, or times 1/10 times 1/10, which is 2.5 times 1/100th, which is 2.5 divided by 100, which is basically 2.5 divided by 10 divided by 10, which simply means we've moved the decimal twice to the left, and that's that. So if we have a number with a times 10 to a positive integer, we have a larger number. And if we have it to a negative integer, that number is smaller. Okay? 2.5 times 10 to the 0. Remember, 10 to the 0 is simply 1. So anything times 10 to the 0 is just whatever it is, 2.5. So let's look at converting from decimal notation to scientific notation. When you do that, we're going to put the decimal after the first number, boom, right here. And then we have to figure out how many times we have to move that decimal. Okay, so basically we have 3.89 times 10, and this number is bigger than 1, so that means the power, our end value, is going to be positive. You can see we got to go 1, 2, 3, 4, 5, 6, 7, 10 to the 7th. So 3.89 times 10 to the 7th is the same as the number we were given here. Okay, 3.89 multiplying by 10 7 times would get us back to this number. Okay, so in this one we have a number that's smaller than 1. So we're going to put our decimal still between after the first number. That's 1 there, right? So 1.6 times 10. And in this case, we have to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places to get it over there. And in this case, the number is less than 1, so our power is going to be negative. So 1.6 times 10 to the negative 11 is the same as this value. Okay, 1.6 divided by 10 11 times gets us back to this number. That's how we're going to go from scientific notation to decimal notation, or from decimal notation to scientific notation. Okay, these numbers are the same. 389,000,000 is the same as 3.89 times 10 to the 7th. Okay, and you can see why we would write it like that, because if we were copying that number, we could easily drop a 0 or add a 0, especially as there's more zeros. Okay, so we write those numbers in scientific notation, so it makes it easier to write, it makes it easier to copy. All right, so from our metric system table, it shows us that 1 kilometer is equal to 1,000 miles. 1,000 meters, not miles. 1 kilometer is 1,000 meters. We can see that from, we have kilo, and kilo means 1,000. 10 to the third. So 1 kilometer is 1,000 meters, or 1 times 10 to the third meters. So 1 kilometer is 1,000 meters, which is the same thing as 1 times 10 to the 3 meters. Okay, so 1,000 and this are the same thing. So the example is the kilometer is 1 times 10 to the third meters. Okay, example 2, here we have 1 PL. And we see P means pico. L means we're measuring in volume. A picoliter is going to be really small, right? Because these are units smaller than the base unit. Our base unit is liters. Pico means that, which is 10 to the negative 12th. So 1 picoliter is equal to 1 times 10 to the negative 12 liters. So picoliter, if we take a liter and divide it, what is that? 1 trillion times equally, one of those little volumes would be a picoliter. So pico is really small volume. So picoliters, when we're dealing with very, very small volumes, the average volume of a red blood cell is about 0.1 picoliters. So a red blood cell, very small. All right, so practice. Let's do a little bit of practice here. So what I would do right now is pause the video and try to do these yourself. And then come back and I will go through them and give you answers. But pause for a second, do them, and come back and check with me. Okay, so hopefully you've done them now. Let's go through these real quick. So how many microliters are related to liters? Let's go up to our table here real quick. And I've also provided you a conversion sheet that you can just print off and have in front of you, so you can have this table and the other couple tables that are associated with conversions right in front of you when you're doing these. Okay, so micro, right here. Micro is that weird shaped U, the Greek U. Micro means 10 to the negative 6th. So 1 microliter would equal 1 times 10 to the negative 6th liters. Okay, that's how we're going to use that table. How are gigameters, so we're doing length here, related to meters? Again, we go up here and we see giga, and giga means 1 times 10 to the 9th, so that's 1 billion times bigger than a meter in this case. So 1 gigameter, remember meters lowercase m, but giga's capital G, is equal to 1 times 10 to the 9th meters. So a gigameter is 1 billion meters. It's a very long length. Okay, the last thing we're doing is complete the following table. We're going to convert between decimal notation and scientific notation. Remember or scientific notation and decimal notation. We'll go back and forth. So remember, when we have decimal notation, we're going to scientific notation. We're going to put our decimal after the first number. So in this case, we have 4.5 times 10. And this number is bigger than 1. So that means our power is going to be positive. We have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 times to get our decimal over here. So 4.5 times 10 to the 9th. Those two numbers are the same, right? If I take 4.5 and multiply by 10 9 times, I get that back. Okay, going the other way. I'm giving scientific notation. 6.077 times 10 to the 4th. Okay, or 10 to the negative 4th. Negative 4 means we have to take the number in front and divide by 10 4 times. Dividing by 10 is going to shift our decimal to the left. So 1, 2, 3, 4. And our decimal is going to go right there. So I'm going to put a 0 in front. 0, 0, 0. 6077. So we're going to have 0.0006077. That is how we would write that number in decimal notation. Okay. 1.4 times 10 to the 5th. We're going to take 1.4 and multiply by 10 5 times. So 1. So we're going to move that 5 times, right? 4, so that's moving the decimal once. 0, that's twice. 0, that's 3 times. 0, that's 4 times. 0, that's 5 times. So if the decimal is here, 1, 2, 3, 4, 5. Okay, we don't put a decimal there. We've moved it. So it would be 140,000. 1.4 times 10 to the 5th is 140,000. Okay, we have decimal notation, and we need to go to scientific, so it means we're going to put the decimal here. So we're going to get 7.307 times 10, and this number is smaller than 1, so it's going to be negative power. We have to move the decimal 1, 2, 3, 4, 5, 6, 7 total times. So 7.307 times 10 to the negative 7. Those two numbers are the same. Last one, that should be a decimal, not a comma. 5.2 times 10 to the negative 2. Negative 2 means we divide by 10 twice. So that would mean moving the decimal 1, 2. That would end up there. So we'd have 0.052. Okay, so 0.052 is the same as 5.2 times 10 to the negative 2. Okay, so hopefully you got those and you're getting this. If you're not, feel free to come and see me and we will talk about them.